Nanomaterials with exceptionally high surface areas are critical in fields like catalysis, energy storage, gas absorption, and water purification. These materials often possess surface areas measured in hundreds to thousands of square meters per gram, meaning that a few grams of material could theoretically cover an entire football field. This remarkable property arises from nanoscale porosity, layered structures, or specific chemical architectures. A single gram of graphene oxide, if unrolled and spread out, could theoretically cover an area equivalent to 4 football fields. It's like crumpling a massive blanket into a small box. The material's true size becomes evident only when fully unfolded. 2 covalent organic frameworks, COPs, designed precision at the nanoscale. Explanation COPs are crystalline materials composed of light elements, CHOB, linked by strong covalent bonds into 2- or 3-dimensional frameworks. Their well-defined pore structures and exceptionally high surface areas, often exceeding 5,000 meters per grams, make them ideal for gas storage, separation, and catalysis. COFs are used to capture and store hydrogen and methane gases, providing compact and efficient storage solutions for clean energy applications. Analogy: COFs are like Lego structures built with nanoscale precision. Each block can be customized to create a material with specific properties and applications. 3. Activated carbon, the workhorse of adsorption explanation. Activated carbon is a porous form of carbon with a high internal surface area, often exceeding 1,500 meters per gram. It is produced by heating organic materials such as coconut shells or wood in the absence of oxygen. The activation process creates a network of micropores and mesopores, which are highly effective at trapping pollutants, gases, and impurities. Activated carbon is widely used in water filters to remove organic contaminants, chlorine, and heavy metals through adsorption. Analogy: it's like a sponge at the molecular level, capable of trapping and holding impurities within its vast network of pores. Zeolites are crystalline aluminosilicates with a highly ordered microporous structure. Their uniform pore sizes and high surface areas, 500 to 1,000 ms per gram, enable selective adsorption and separation of molecules based on size and polarity. Zeolites are essential in catalysis, such as cracking hydrocarbons in oil refineries, and in environmental applications like CO2 capture. In industrial settings, zeolites are used to separate nitrogen from oxygen in air separation processes for medical oxygen generation. Zeolites are like molecular sieves, selectively allowing certain molecules to pass while trapping others based on size or chemical properties. Aerogels are ultra-lightweight materials derived from gels, where the liquid component is replaced by air. With surface areas often exceeding 1,000 meters per gram and porosities above 90%, aerogels are excellent insulators and adsorbents. They combine extremely low density with high strength and surface area, making them versatile in aerospace, thermal insulation, and filtration. NASA uses silica aerogels for capturing cosmic dust particles during space missions due to their low density and high impact absorption. Aerogels are like a solidified cloud, light, porous, and capable of holding incredible amounts of material within their vast internal spaces. Carbon nanotubes, CNTs, are cylindrical structures composed of rolled graphene sheets. They have extraordinary surface areas, up to 1,000 meters per gram, and remarkable mechanical, thermal, and electrical properties. CNTs can be single-walled or multi-walled, MWCNT, with applications ranging from energy storage to drug delivery. CNTs are used in supercapacitors, where their high surface area allows rapid charge and discharge cycles with excellent energy density. CNTs are like rolled-up carpets, where each layer provides additional surface area for interaction, despite their small size. Graphene oxide, GO, is a chemically modified form of graphene with oxygen-containing functional groups, enhancing its dispersibility in water and ability to adsorb ions and molecules. Reduced graphene oxide, RGO, is partially restored to graphene-like properties through reduction processes, offering a balance between functionality and conductivity. Both materials exhibit high surface areas, or 1,000 meters per grams, and are used in catalysis, energy storage, and sensors. GO is used in water purification systems to absorb heavy metals and organic pollutants due to its high surface area and functional groups. GO is like a highly functionalized sheet of paper, capable of folding, stacking, and holding molecules due to its surface chemistry. Mesoporous silica features well-defined pores in the 2 to 50 nanometers range, with surface areas often exceeding 1,200 meters per grams. It is synthesized using templating techniques, where surfactants create uniform pore structures. Its thermal stability, tunable porosity, and biocompatibility make it valuable for drug delivery, catalysis, and adsorption. Mesoporous silica is used in drug delivery to encapsulate and release therapeutic molecules in a controlled manner. It's like a honeycomb, where each cell can store and release specific substances depending on its design. Nanoporous polymers are organic materials with a high density of interconnected pores. These materials combine lightweight flexibility with surface areas comparable to inorganic counterparts, 1,000 ms per grams. Their chemical versatility allows the integration of functional groups for specific applications, such as gas storage or chemical separations. Nanoporous polymers are used in hydrogen storage, where their high surface area and lightweight nature enable efficient gas adsorption. It's like a sponge that can be squeezed and reshaped, maintaining its ability to absorb and release substances as needed. These materials are indispensable in modern science and technology due to their unique combination of high surface area, tunable porosity, and chemical functionality. Energy storage, CNTs and RGO in supercapacitors and batteries. Environmental remediation, activated carbon and GO for water purification. Catalysis, zeolites and mesoporous silica as catalysts in chemical reactions. Gas storage, MOFs and nanoporous polymers for hydrogen and methane storage. Drug delivery, mesoporous silica and aerogels for controlled drug release. Hydrogen storage systems based on MOFs and nanoporous polymers are enabling advancements in fuel cell technologies for clean energy. These materials are like molecular toolkits, each designed for a specific task, offering unparalleled efficiency and functionality at microscopic scales. Nanomaterials with high surface areas exemplify the power of engineering at the nanoscale. Whether trapping pollutants, storing energy, or catalyzing reactions, these materials demonstrate how manipulating matter at the atomic level can yield extraordinary macroscopic benefits. From covalent frameworks to porous polymers, the versatility and functionality of these materials continue to revolutionize science and industry.